The Immersive Digital Experiences Alliance is a non-profit industry association developing a family of royalty-free technical specifications to enable the digital future. Our members bring world-class experience in light field and holographic imaging, distribution networks, and content creation. You can learn more at immersivealliance.org. The IDEA Specialized Contract Track consists of 8 segments covering all aspects of immersive media. In this segment, you'll get a glimpse of the future of mobile mixed reality.
Hi, my name is Bhaskar Banerjee. I am the co-founder and CTO of GridRaster. Today I'm going to talk about the future of mobile untethered mixed reality. Over the years, we have seen different use cases of VR and MR in using mobile devices. Here on the left, we see, for example, the Pokemon Go video game, which is fairly popular, running on mobile devices. You have some video games running on VR headsets like the Oculus Quest and Oculus Rift. On the right, you see some examples of mixed reality experience on a tablet where someone is placing a piece of furniture using the IKEA app or getting directions using the Google Maps, or in enterprise use cases where someone is getting work instructions using the Microsoft HoloLens. So we've kind of moved from simple animation for simplistic video games to rather complex photorealistic rendering on devices for immersive experiences. Now, in order to make a truly immersive mixed reality experience, we require high quality visuals fused to the real world. So there are 3 challenges that we need to solve in order to do that. One is, of course, rendering, where we are trying to render very high resolution content at high frame rates with extremely low latency so that immersive experience can be maintained. We need to do full spatial mapping so that we can understand what object is actually there in the scene, what's the actual physical world look like, and if you want to render an object, place it in a particular location at the scene, what exactly is that scene made of. So we require scene segmentation, understand the objects, and generate a mesh of the entire scene. And then we combine the 2 using localization and position so that we can align objects, anchor it stably in the world, and have the correct occlusion where someone needs to be behind something else. We can accurately do so. In order to actually do high quality near photorealistic rendering, we require extremely high resolution displays, and none of them are really there in mobile devices right now. Ideally, in order not to be able to distinguish the pixels, we need resolutions as high as 8K per eye. So it's extremely high resolution display. In order to maintain realism, that you don't have any motion sickness, we need less than 16 milliseconds motion to photon latency. All this together with 90 frames per second or higher, and rendering extremely complex polygons, which are in hundreds of millions of polygons, it requires extremely high end GPU for that rendering to happen. Not to mention, you require extremely high quality textures and raycasting and estimation of lighting and all that. And this basically requires extremely high end GPU to be able to render that, which is comparable or better than what we are used to for AAA gaming. The other component is scene understanding, where we use the cameras on these devices, both the RGB color camera and the depth camera, to map the entire world, do a full 3D reconstruction, followed by segmentation of the scene, generating the mesh, and doing a full object identification and registration. So the above image shows you a capture of our office. This is entirely point cloud. From here, we actually have to focus on the table where, let's say, the objects of interest are placed. Then we divvy that up. We segment the scene into the individual objects, find the mesh, and then isolate the object of interest out of the scene, as you can see in the bottom right, where we are isolating the model that we have in the center. So All this, again, requires extremely high-end GPUs for running the 3D reconstruction, running the deep learning algorithms, and 3D computer vision required to do the scene understanding. Once we have these two components in place, we need to be able to localize and position the object. We need to be able to run the SLAM algorithms to achieve millimeter accuracy in overlapping of the object of interest with the model that we are rendering on top of that. We need to have continuous 3D object registration as you move around in 3D. So it's a full 6-stop experience. So you need to have a continuous estimation of the pose with which you're looking at the object, and more so in a cluttered environment where you're able to isolate objects of interest from rest of the scene. So again, all of this requires high-end GPUs for reconstruction, deep learning, and 3D computer vision. So what we're saying is we require very high-end GPUs to be able to do the rendering of complex objects containing hundreds of millions of polygons in high resolution. We require high-end GPU to be able to run 3D computer vision, deep learning, to do 3D reconstruction, spatial mapping, and running all our SLAM algorithms. So we want this kind of a GPU on devices which you're going to wear on your head, like the Oculus Quest or the Microsoft HoloLens. And this requires a lot of power, generates a lot of heat, and they're heavy. So can we do that? Well, we can't. We can have these devices run a cable from the headset to a PC, having this kind of a GPU in there, but then we are basically tethering to that PC. So none of them is actually the solution that we want. In some specific cases, maybe tethering will work, but by and large, we want an untethered wireless experience where we can move around in 6DoF. What we propose and what we actually do in our GridRaster platform is we run the heavy lifting of all the GPU intensive compute on the server. So we run it on a server which connects by Ethernet to a wireless switch, or it can actually connect to an LTE or a 5G access point. And any device that you're going to wear on the head or carry around as a tablet or a mobile device, you will actually connect by wireless. And there is a constant back and forth of raw data going from the device back to the server and rendered frames from the server back to the device. So the device is actually running a client app, which is a thin client, and you have all the raw sensor data, like the RGB depth data, IMU sensor data, the inputs that the users provide, the gestures, the pose, the gaze, the eye tracking, etc. Everything is actually fed back straight into the server. And from the server, we render the frames, we do all our fusion of the real and virtual worlds by doing 3D AI computer vision for spatial mapping and scene segmentation. All these algorithms run on these servers. So you can actually render the frame accurately and send it to the device. Now, one of the challenges here is the latency that is inherent in sending data up through the network to a server and back to the device. And we have on-device reprojection and wireless buffering and wireless link optimization to minimize that impact. So we have technology that can hide the latency by about 100 milliseconds or so. So you could be 120 milliseconds away and yet see motion to photon latency of less than 16 milliseconds. So this is the solution that allows you to render complex high fidelity 3D models on these headsets without having to tether to the device, without really having to weigh it down with high-end GPUs or any of the necessary requirements that we need to make the immersive mixed reality possible. So we are providing this complete end-to-end solution, leveraging the hybrid computation of the server and the local device. And this allows us to basically input all sorts of CAD data, all sorts of animation data that we can input from from our customers' models and render it out onto standard headsets like the Microsoft HoloLens, Oculus Quest, or Apple's iPad, for example. Let's look at a couple of demos to kind of elucidate the point. Here is a GridRaster demo running on the Microsoft HoloLens. We see a model of a turbo engine with its different components here, and that you can basically tap and visualize, go closer, take a look, understand what the different components do, and you can actually visualize objects which are extremely high polygon content. So this one, for example, is using a turbo engine model which is 18 million polygons running on the HoloLens. And as you can see, you can put it in a desired location that you want, manually place it. You can run different annotations on it. You can change color. You can sketch on it. You can measure point-to-point distance in between 2 points of this device, as shown here. So there are a lot of interesting things you can visualize and do, provided you can visualize them with high fidelity on these devices. One of the key issues most of our customers talk about is going from CAD models to devices is a time-consuming and extremely difficult process, because what they have to do is take a CAD model, tessellate that, and that leads into models which are hundreds of millions in polygons, and none of these devices can natively fit that. So they now have to decimate the model to bring it down to a few thousand, maybe 100,000 polygons that these devices can accommodate. And in doing so, you basically either lose significant feature details of the CAD model, or you have to manually start adding and subtracting parts that you require to visualize. So you're basically making the model smaller and smaller. So either of these two tasks take a lot of time, and you lose the fidelity that you really need to see. So what our technology allows us to do is we can fully visualize in 3D large complex objects. Like, as I mentioned, this is about 15 million polygons. You can go from scene to scene. You can load different components, different parts, and you can also look inside. You can do things like sectioning 3D objects and see inside that how it looks like. And there are lots of other applications, use cases that you can provide. You can provide work instructions. You can make rapid iterations now, because you don't have to decimate and bring down the polygon content as you're changing your CAD model. You can iterate very fast from changing the CAD model and bringing it down into the HoloLens directly from the server. So the server that you're using to render your CAD can actually be used to render out onto the HoloLens with basically the same GPU capability as a high-end desktop PC. So this is for just purely rendering. The other aspect, as I mentioned, is alignment of objects, understanding the object, the spatial mapping. Here we are looking at a CAD model of a 3D printed lander model that we have, and as you can see, once the user looks at the lander, it registers the lander and aligns itself automatically in 3D, and now you can walk around it and see that it is fixed there. A little bit of jitter that you see in the video is because of Microsoft Mixed Reality Capture working only at 30 frames per second, because part of the effort, part of the work done by the graphics card is to save the video. But if you actually wear the device and see, this will run at 60 frames per second, so it'll be pretty smooth. So these are like the two examples that I can show, which elucidates what we can accomplish on these headsets, which are fairly limited in compute, to do extraordinary amount of computation on the server and make it useful for these kind of applications. So So this is kind of to summarize what we can accomplish and where we see this going into the future. We can render extremely large models, either CAD models or scenes with extremely large number of polygons and points of the point cloud that can be rendered directly onto the device without any decimation. You don't have to cut down your scene to fit into these devices with the help of rendering from a server. So this allows for quick iterations, high frame rate, high fidelity rendering, and you can use it for a whole bunch of use cases. You can use it for training using live training manuals with the 3D instruction set. You can use it for design and manufacturing with precise alignment of virtual and real objects. Repair and maintenance, again, because you see it in 3D, it's like having a live 3D version of YouTube running in front of you with real 3D instructions. So you have very little error in instructions that you carry out, and also if there are any defects and if there are any errors between the 3D world, what you have designed versus the one that you have manufactured, you can actually do detection of such errors. And multiple users can wear the devices and have a shared world experience, which allows for collaboration, review, and analysis. To summarize the performance, if you take a simple Microsoft HoloLens 2, which is state-of-the-art mixed reality headset, and run our solution on top of that, we can actually render 60 million polygons on these devices with a single graphics card on the server, whereas the device is kind of saturated about 100,000 if you run standalone locally on the device, maintaining extremely high frame rates, 60 frames per second or higher. Motion to photon latency is maintained at sub 20 milliseconds. Full 3D spatial mapping, there is no limitation as to how fast and how accurately we can map it because we are not using the limited GPU. We are running it on the server, so you have the dedicated GPUs. And again, because of high precision of the mesh, we can actually render it with an extremely high precision as well. So we are rendering it with 1 millimeter precision, which is only limited by how precise the device rendering is. So all of this allows us to foresee a future of mobile mixed reality where you can put together very high quality, very complex 3D scenes in near photorealistic experience on headsets, which can be thinner, lighter, and that's more comfortable to wear for long periods of time. You're making them thin clients. You're using it as raw display and raw sensors to just collect the data and processing it pretty much entirely on a server farm, which allows for really immersive mixed reality experiences. I hope you enjoyed this talk. Thank you.
Thanks for joining us in this segment from the Immersive Digital Experiences Alliance. IDEA is a nonprofit industry group developing a family of royalty-free technical specifications to enable the digital future. You can learn more at immersivealliance.org. You can join IDEA, download the ITMF specifications or white paper, or just join our mailing list to stay informed. Thanks for joining us today.